Okay now? See you. I will tell the definition of the continuous function. A function f maps from closed interval a comma b to r is said to be continuous function at a if for all epsilon greater than 0 there exists delta greater than 0 such that mod f of x minus f of a less than epsilon whenever mod x minus a less than delta. This is the definition of the what? Continuous function. Understand? Okay, fine. The next, uniform continuous. Uniform continuous function. A function f maps from closed interval a comma b to r is said to be uniform continuous on S subset of R if for all epsilon greater than 0 there exists delta greater than 0 such that mod f of x1 minus f of x2 less than epsilon whenever mod x1 minus x2 less than delta for all x1 comma x2 belongs to S. Belongs to S. This is the definition of the what? Uniform continuous function. Now I will tell a related theorem of continuous and uniform continuous. I am writing the statement, right? A function f maps from closed interval a comma b to r is continuous at a if and only if f is uniform continuous on S subset of R. Right? In this theorem, two parts are there. Taking continuous, you are forming uniform continuous. Second part, taking uniform continuous and showing what? Continuous. Right? Fine. I will do proof here, right? No. Part 1. What is the part 1? If f is continuous f is continuous at A, then to show that what? F is uniform, continuous at S subset of R. S subset of R. Right? Fine. It is enough to show that for all epsilon greater than 0, there exists delta greater than 0 such that mod f of x1 minus f of x2 less than epsilon, whenever mod x1 minus x2 less than delta for all x1 comma x2 belongs to S. This one we have to prove. Understand or not? Okay. Since f is continuous, given condition, right? F is continuous at A, that is for all epsilon greater than 0, there exists delta greater than 0 such that mod f of x minus f of a less than epsilon, whenever mod x minus a less than delta. This is the condition of the what? Continuous function. Give equation number 1. Right? Okay? Fine. Now, consider mod f of x1 minus f of x2. This one I will show that less than how much? Epsilon. Right? Fine. This is equal to. In this, what I will do here, adding and subtracting f of a. Right? Fine. What I did here? Adding and subtracting f of a. Right or not? Okay, fine. Same result you are getting. Right? Fine. This is equal to, I am writing this one in 2 parts. Right? I will separate this one. When you are separating, you are writing less than or equal to mod f of x1 minus f of a plus f of a minus f of x2. What is our condition? Since mod a plus b is less than equal to mod a plus what? Mod b. Have you understood or not? Okay, fine. This is less than or equal to mod f of x1 minus f of a. Inside mod, second value and first value can be interchanged. There will not be any minus plus. You are writing any minus, you are taking minus common here. So what you are getting? It will be positive only. Right or not? So I am writing this one. F of x2 minus what is that? F of a. Have you understood now? Fine. From equation 1 here, equation 1, f of x minus f of a, how much? Less than epsilon. Here two parts are there now. For each part, how much you can write? Epsilon by 2. So this is less than of epsilon by 2. So since from 1, mod f of x minus f of a less than epsilon. Or you can write, it can be written as epsilon by 2. Epsilon by 2. Right or not? Okay, fine. So how much you got here? You got epsilon. On the left hand side, what is that? Mod f of x1 minus, what is that? x2. Then above, mod x1 minus x2 less than delta for all x1 comma x2 belongs to what? Yes. This only we have to prove. Yes. Right or not? Therefore, if it's uniform, continuous on S subset of, hence proof. Part 1 is over. The next we will prove the what? Part 2. Now what I will do? Part 2. Part 2 I will prove here. Part 2. Part 2. What is the part 2? Are you understanding? Huh? If f is uniform, continuous on S subset of n subset of R, then to show that what? F is F is continuous function vector A. Right or not? It is enough to show that for all epsilon greater than 0 there exists delta greater than 0 such that mod f of x minus f of a less than epsilon. Whenever mod x minus a less than delta. Right or not? Okay, fine. Since f is uniform continuous on a subset of R. For all x1 comma x2 belongs to what is that? S. This implies mod of x1 minus x2 is less than delta. Mod value in between the 2 points always what? Very small number, positive number. The positive number I have taken what is that? Delta. Even also given condition to us for the uniform continuous, right? Fine. Suppose x1 is variated to x and x2 kept constant to what? A. This implies mod f of x1 minus f of x2 less than epsilon can be written as f of, instead of x1 what can I write? And instead of x2 what you have to write? A. Less than epsilon whenever mod x1 minus x2, x1 means x, x2 means what? A less than what? Delta. This is the condition of the which one? No, continuous function. Continuous function. Therefore, f is continuous at the hence proved. Hence proved. Oh.